All right, in our next unit, we're going to take a look at nuclear chemistry. So this is related to atomic structure. I'll also be doing a little bit of review of some of the topics we learned a long time ago. And we'll start off with the difference between a chemical change and a nuclear change, or chemical reaction versus a nuclear reaction. So starting off with chemical reactions, not often, always the changes are results of something to do with the electrons. So electrons are being transferred, electrons are moving around, and so the changes always involve electrons. And during a chemical reaction, the elements do not change into other elements. So you start off with carbon and hydrogen and oxygen, let's say, in the reactants. You end up with products that still contain carbon and hydrogen and oxygen, just different forms. Interestingly, relatively small amounts of energy are involved in chemical reactions. Even thinking about the most exothermic reactions, it's relatively small in terms of the amount of energy, especially compared to nuclear reactions, as we'll see in a little bit. The speed of the reactions, chemical reactions, depends on things such as concentration, temperature, catalysts, or pressure, things that we've talked about, factors that affect the rate of a chemical reaction. Now let's compare that to nuclear reactions. As the name implies, a nuclear reaction involves changes to the nucleus. And in this case, the elements involved in the reaction do change into other elements. So this is not alchemy per se, but we do have elements changing into other elements. And again, as we'll see later, some nuclear reactions release a tremendous amount of energy. So more energy is involved in nuclear reactions than chemical reactions. Something that may be important to note is that all nuclear reactions are first order, and therefore the rates of nuclear reactions are not affected by external factors such as temperature and pressure, maybe concentration, but not temperature and not pressure so much. All right, so we have a couple different types of nuclear reactions that occur. Some occur naturally and some are induced. And in either situation, we have particles and or energy that is given off during this process. And those particles and or energy are known as radiation. So radiation or radioactivity. So radioactivity is really a term more for the behavior of a substance, the property of a substance. Something that is radioactive will naturally give off some particles and or energy. And so we'll talk about the different types of nuclear reactions, those that are spontaneous versus those that are non-spontaneous. A little review of the nucleus. Again, our focus is on the nucleus itself and the changes that occur to the nucleus. So of course, inside the nucleus, we find just the protons and neutrons in an atom. So we're not really going to concern ourselves too much with the electrons, though we'll see in a little bit. We will deal with the electrons just a bit. We talked about way back when the nucleus is very small compared to the size of the entire atom. Yet the nucleus contains almost all of the mass. So what does that mean? That means that the nucleus of an atom is very, very, very dense. Now you don't have to know this number, but just think about what that means. 10 to the 18th grams per cubic centimeter. That is pretty amazing, pretty dense object. All right, a couple vocabulary terms here for you. First, nuclide refers to different nuclear structure of all the elements. So nuclide is just a term for describing the nucleus of a particular atom. Versus isotope. An isotope refers to the different nuclear structure of the same element. So if you're looking at one particular nucleus, one particular atom, we call that nuclide. Isotope is all of the elements, so they have the same number of protons, but different nuclear structures because they have a different number of neutrons. So let's look at nuclide symbols, again, describing one particular atom, also known as a nuclear symbol. And so what it looks like is this. We have some number A over some number Z next to some letter or letters E or X. There's different formats for nuclide or nuclear symbols. And so we'll go with this one here. Some number A, that number A, the top number in a nuclear symbol, is the mass number, without units, of course, or the atomic mass without units, or mass number. So mass number, if you recall, is simply the number of protons and neutrons in an atom. The bottom number Z is the atomic number or nuclear charge or charge of that particle. And so, of course, protons are positively charged. So if you had, say, 6 protons in the nucleus, the nuclear charge would be plus 6. So atomic number or nuclear charge. And then E or X is the symbol from the periodic table. Sometimes we use other symbols, such as those for protons and neutrons and electrons, among others. So this is the symbol of the particle. So what determines if something is radioactive? So let me back up a little bit. Radioactive refers to a nucleus, an atom that is unstable and will undergo a process known as radioactive decay, a process where that atom is emitting particles and or energy. Well, there's some situations where we have atoms that are especially stable, and so we'll talk about the stable ones, then we'll get into a discussion about what factors lead to something being unstable. So it says most naturally occurring nuclei have even numbers of protons and neutrons. In fact, there's a table in your book on page 935. And for some particular reason, we have atoms that have special stability when their protons or protons and neutrons are exist in even numbers. In fact, those that have a stable number of protons and neutrons, or both protons and neutrons, are especially stable. And these values, we have these things called magic numbers. They are anything with 2 protons, or a total of 2 protons and neutrons, 8, 20, 28, 50, 82, and 200, and oops, I was thinking about something else for a second. 126, that is. So maybe important to know, again, just know that any atoms that have this number of protons or this number of protons and neutrons are especially stable and are unlikely to undergo radioactive decay. So what are the factors that lead to an atom or nucleus being unstable? So I guess it's implied that if there's an odd number of protons or odd number of protons and neutrons, then maybe that's relatively unstable. There are some other things to consider. Go to page 936 in your books. We have a graph of the number of neutrons versus the number of protons. And so something that is important to note is that most stable low atomic nuclei have an equal number of protons and neutrons. And we're going to talk about this neutron to proton ratio. So for light nuclei, and again, that's kind of a relative term, light nuclei, so we're talking about those that have, I don't know, 20 or so protons in their nucleus, will have a 1-to-1 ratio of neutrons to protons. As atomic number increases, so does that neutron to proton ratio. So what's going on here? So what causes a nucleus to become unstable? Well, we kind of talked about already, the nucleus is really, really, really small. And in this small space, you have lots of like charged particles, meaning protons. And those charged particles don't want to be near each other. They repel each other. And so it's actually the job of the neutrons to help stabilize the nucleus. So we have these strong attractive forces. In fact, it's called a strong nuclear force, attractive force between neutrons and between neutrons and protons, and they will stabilize the nucleus. So again, number two here, as the atomic number increases, that neutron to proton ratio will also increase. So it takes more and more neutrons to stabilize the nucleus as the number of protons increase. So that's one of the factors. You got too many protons inside the nucleus, that's going to lead it to become relatively unstable and susceptible to radioactive decay. Interestingly, number three there are no stable nuclei above atomic number, it's actually above 82, so starting with 83. So anything past lead, there are um, no stable nuclei. Anything that has more than 82 protons in its nucleus will be radioactive. Now be careful. That doesn't mean that anything with less than 83 protons is stable. That's not true. There are atoms that have less than 83 protons that are radioactive, but there are no stable nuclei with more than 82 protons. So these nuclei that are unstable undergo natural transmutation. Transmutation is just a fancy word for turning into a different substance, turning into a different element. Various types of transmutations that a nucleus may undergo will be discussed later. Just reviewing from Chem 1, we're talking about things like alpha decay and beta decay and positron emission and all of those. And again, if we look on that figure in 26.1 on page 936, we see that things that are neutron poor will undergo radioactive decay. Likewise, things that are neutron rich will undergo radioactive decay as well. So there's that fine line between too few neutrons and too many neutrons. So the green dots there, by the way, are known as the band of stability. So those are relatively stable atoms. And again, we can see the black line represents a 1-to-1 ratio of neutrons to protons. So as atomic number increases, that ratio will increase as well, even for stable nuclei. All right, so we can determine relatively how stable a nucleus is by looking at what's called its nuclear binding energy. Now, related to nuclear binding energy is something known as mass defect. We'll get to that in a second. Here's kind of the definition. The masses of atoms are always less than the sum of their constituent particles. So this difference in mass between the sum of the parts and the whole is known as mass defect. Well, the difference in masses between the reactants and products in a chemical reaction is really small. But the difference in mass between the reactants and products in a nuclear reaction is actually fairly large, and that is why we have such a big difference in terms of the energy associated with nuclear reactions versus chemical reactions. All right, so let's see how to calculate mass defect. Go ahead and take a look at example 26.1. I'll read it for you. It says calculate the mass deficiency for chlorine 35 atoms in AMU per atom and also in grams per mole of atoms. The actual mass of chlorine 35 is 34.9689 AMU. So we're going to be given some really precise values for these masses. Now, if you go back a page, the top of page 935, we'll see in a table there we have the masses of the fundamental particles, those being protons, neutrons, and electrons. And so we're going to use those values to help us determine mass defect. So again, we want to take the sum of the masses of the particles And we're going to subtract that from the mass of the whole, and that will give us our mass defect. So again, the mass of the sum of the particles is greater than the whole, so we want to subtract those to get a positive value. So looking at our particular isotope here, we have chlorine 35, which has 17 protons, 18 neutrons, whoops, that should be neutrons, 18 neutrons. And even though electrons are not inside the nucleus, we do use the electrons to calculate nuclear binding energy. So that would be 17. So we take the mass of 17 protons, each with a mass of 1.0073 AMU, plus the mass of 18 neutrons, each with a mass of 1.0087 AMU. So notice that the mass of a neutron is slightly more than that of a proton. When we talked earlier in the year with relative atomic masses and masses of particles, we said for all intents and purposes, the mass of a proton and neutron are equal. Here we see they are slightly different. And then electrons, again, be really, really small, but we're still going to add those, 17 of those, each with a mass of 0.00054858 AMU. And for now, know those values. I may give those to you. I'm not sure just yet. All right, so the sum of these particles is 35.290 AMU. Well, from the problem, we were given that the mass of the whole atom was 34.9689 AMU. Take the difference, that is our mass defect, which is 0.32 AMU. Now take a look at that next setup there. How do we convert from AMU to grams? Well, what is the relationship between an AMU and a gram? If you take an AMU and divide it by Avogadro's number, you will get a mass in grams. Now, why is that? Well, think about, say, carbon. Carbon has a mass of about 12 AMU. That's one atom. A mole of atoms has a mass of 12 grams. And so the relationship there has to do with Avogadro's number. So anytime you want to convert AMU to grams, take that value and divide it by Avogadro's number. So here we see, again, the setup's a little funky, 0.321 grams per mole. So it wanted it in grams per mole of atoms, not just grams. If we were finding just grams, take that mass defect in AMU divided by Avogadro's number, and that'll give you a mass in grams, which will be really, really, really small, 10 to the negative 20 something mass in grams. This will be important for some calculations that we do later on. So what happens to this mass? You can't just create mass, can't destroy mass. This mass is actually converted to energy. So the mass defect is used to determine something called the nuclear binding energy. Nuclear binding energy can be interpreted, I guess, a couple different ways. One, the energy released when the protons, neutrons, and electrons come together to make the atom, or also the energy required to break apart an atom. We're going to use Einstein's equation to calculate nuclear binding energy. So E, of course, is the nuclear binding energy in joules. M is the mass defect in kilograms. So we're often going to calculate mass defect in AMU, convert that to grams, convert that to kilograms, plug that in. And of course, C is a constant. It is the speed of light, 300 million meters per second. All right, take a look at example 26.2. It says, calculate the nuclear binding energy of the chlorine 35 atom that we discussed in example 21.1, 26.1 rather. Wants it both in kilojoules per mole and kilojoules per gram and mega electron volts per nucleon. We'll just probably do the first couple. So we take our mass defect, which was 0.321 grams per mole. And again, that's per mole of chlorine atoms. So since we already have the value per mole, we're just going to use that and convert it to kilograms per mole. Plug that in for M. Multiply that by the speed of light squared, and we get our nuclear binding energy. Look at the units there. It says kilogram meter squared per second squared, which is the same thing as a joule. So this will give us our answer in joules per mole. Divide that by 1,000, and we get our value in kilojoules per mole of chlorine atoms. So it's probably sometimes better to express the nuclear binding energy in kilojoules per gram, sometimes per mole, sometimes per nucleon as well. Nucleon just refers to the protons and neutrons in an atom. So this one here, we got our nuclear binding energy in kilojoules per mole. Use the molar mass of chlorine to find that value in kilojoules per gram. And go ahead and disregard letter C. All right, your turn. Go ahead and do exercise 15 on page 964. We're going to calculate mass defects a couple different ways and then use that to find the nuclear binding energy. So go ahead and pause and do that now. All right, so here is our setup. Take the sum of the parts. So we got 46 protons, 62 neutrons, and 46 electrons. Using their masses, we add all of that up. So the sum of the parts is 108.9004. I think we want 4 digits after the decimal in our answer when we're adding those values. The actual mass of this isotope was given to us, 107.90389 AMU. And the difference is our mass defect, 0.9965 AMU. That is per each atom. And so it wanted that value. It also wanted the value in meaning the mass defect, in grams per mole. Again, this work obviously is rather unnecessary. So your value in AMUs per atom will be the same as the value in grams per mole. So 0.9965 grams per mole of these atoms. Right, take that value, convert it to kilograms per mole. We can just plug in kilograms too, like I said before, and you can convert to moles later. I chose to do the moles first, so this is kilograms per mole. And so notice I took that value, 0.9965, just divided by 1,000, multiply by speed of light squared, and we get 8.97 times 10 to the 13th kilogram meters squared per second squared per mole, aka joules per mole. I believe it wanted the answer in kilojoules per mole, so take that divided by 1,000, and we get 8.97 kilojoules per mole. Look at figure 26.2 on page 939. So this is a plot of binding energy versus mass number. And so we see relatively large and small nuclei are more unstable than nuclei of intermediate mass. So nuclear binding energy gives us an indication of relative stability. The higher the nuclear binding energy, the more stable that nucleus is. And so we can see here that according to this table or this graph, iron is the most stable nucleus on here. It has the highest nuclear binding energy. All right, that concludes this lesson. Next time we'll talk about nuclear equations. Thanks for watching.